let's get to the problem. A, compound 2 is a powerful nucleophile. We're talking about this. And for our purposes, we will treat MgCl plus as a counter ion. The transformation of 2 into 3 is accomplished via an SN2 type process. Draw a mechanism for this process and identify the leaving group. Okay, if we know that's a nucleophile, then we know the other structure must be substrate. And comparing 2 and 3, I need to have this at least. In other words, we need to kick this guy off. So you can see that the green bound region has to be leaving group that's attached to our substrate. So having said that, let's draw the curved arrow. So because we are undergoing the SN2 reaction, the nucleophile is gonna attack our electrophilic center, which gonna be oxygen here, because we have to form a bond between this triangle and that oxygen. Okay, and then in turn we're gonna have a simultaneous step that shows the leaving group of our acetate ion. Okay, this part, the leaving group must be acetate ion, so we identify part A as leaving group is acetate ion. Okay, and this is like a CH3 if you forgot, and we have a carbon over there, but normally we don't want to write like that, so I'm gonna leave it as just bond line. Okay, and so we identify the leaving group and we drew the curved arrow mechanism to show this is SN2. Just for clarity, I'll write the SN2 above. And let's tackle B. We'll explain why the conversion of 2 to 3 is an irreversible process. Well, the easiest way to see is our acetate ion now is going to act as a nucleophile to go back to compound 2. And it also implies that the conjugate base of the cyclopropane is really strong. In other words, we have we don't see something like weak base to strong base. And you might ask, how is this strong base? Well, then think opposite. When you just add a hydrogen over there just to acidify it, you're gonna have simply alkane structure of this plain cyclopropane. Anything with just CH group like that is hydrophobic and it's a really weak acid. Okay, if it's a very weak acid and when we deprotonate one, then it's going to be really strong base, and that's not really probable. Therefore, this has to be irreversible. Again, the nature doesn't prefer to go to strong base. The same applies when you have a sulfuric acid in water, just as an example, and you will never see this structure in the solution. You will always see H plus and this, and when it goes through another deprotonation, meaning since this is a diprotic acid, you will see further of this. So it's always dissociated. That's why we have just one single arrow instead of the equilibrium arrow. So hopefully that was clear to you guys, and now I'm gonna move on to part C. Okay, so under aqueous acidic conditions, 3 can be converted into 4 either via an SN1 process or via an SN2 process. Draw a complete mechanism for each of these pathways. When we draw the energy profiling diagram, SN2 has simply one hump, and then SN1 has two hump. I believe that the first hump is higher, yeah, and it looks something like that. So this is SN2, that's why we have a one step, and here we have a two step, because there is a leaving group that determines our activation energy. And then we're going to have a carbocation intermediate, and then finally there will be nucleophilic attack. So starting with SN2, we're going to have a simultaneous process in which the leaving group and the nucleophilic attack happens at the same time. So let's see, 3 to 4, I'm going to draw our reactant for this process, and then we have our reagent as an acid. Okay, looking at this, we need to identify who is going to be attacking who. First, we need a proton transfer, because this alkoxide over here is not a good leaving group, just like the alcohol is not a good leaving group. So to achieve that, he's gonna first grab that hydrogen and then create our neutral water as a leaving group for now, and then we're gonna have a very unstable structure that need to kick this out. So we have plus charge here, so we're gonna have water that comes by and then attack this carbon. So you can see that that's kind of like a delta plus due to the induction effect, and then he's gonna come and attack that carbon and then kick these guys out. Then we're gonna have this, and then water will just cleave up that hydrogen one more time, and now we have a happy cyclopropanol. So we're gonna have that. So that's SN2 though, and we have to answer it with SN1 as well. For our SN1, we'll first have again water, the acid. Acid is provided, and our oxygen from here is going to come and attack, or actually abstract the hydrogen. So again, it's the same process as the SN2. Remember, this is like the preparatory step, or this is not the main step, but it's like a introductory step, so that we have a good leaving group. And then we're gonna have this. Now this is gonna just take a one step, because this bond needs to be broken over here. So he's gonna donate the electrons. And there we go. This is what we have. And then in turn, we're gonna have this. We see 1, 2, 3. 1, 2, 3, and we have 4 carbons, and we have 4 carbon here. Because we just donated the electron to get oxygen, now we have a carbocation in this structure. Okay. But this is unstable, so we're gonna have a water that comes along and then donate actually it's going to attach and then lose that hydrogen. Okay, so that becomes simply this now. So this is a byproduct, and this is desired product. And the same thing happened in our SN2 as well. I didn't draw that. I just ignored this part where it just got clipped up. So you see the similarity here. You see that this part is corresponding with this part. And that answers our part D. During conversion of 3 to 4, another alcohol is formed as a byproduct. Draw the structure of this alcohol. So since we've done it, and it matches for both SN1 and SN2, therefore I'm just going to draw it as this. Okay, there's no stereochemistry because we have a same substituents in not only 2 but 3, so you can just draw it like this. However, the carbon is still sp3, so the bond angles are going to be relatively similar to each other, 109.5 degrees.